Exercise number 24 gives us a vector field and a curve C defined by a parameterization here, this vector function r of t. And it has two parts. We are first asked to find a function small f such that big F is equal to the gradient of small f. And the second part is to use part A to evaluate the line integral along C of f dot dr. So part A is basically asking us to find a potential function for the vector field. Now we note that this vector field is a function of x, y, and z and has three components. When we only have a function of two variables with two components, so we're working in R2, we will often check to confirm that the field is conservative before proceeding to look for a potential function. We can do that here, but it is a little bit difficult to keep track of the bookkeeping with only the tools at our disposal, because we would need to consider not only making sure that the partial of p with respect to y is equal to the partial of q with respect to x, we would also have to check all of the others, like the partial of p with respect to z would have to equal the partial of r with respect to x, and you would need the the partial of q with respect to z would need to equal the partial of r with respect to y. Does that cover all of them? That might be it. But making sure that you get all of those and working them all out is a little bit of a pain. And there's an easier way to handle that bookkeeping that we will see in a couple of sections. So temporarily, for right now, for the purposes of this section, we don't need to worry right now about how we test to see whether our field is conservative. We're just asked to find the potential function. So we'll just dive into that, just sort of having faith that this will work. So as I did before, I'm going to work this out rigorously first, and then show you an example of doing this with that quicker sort of shortcut method. It might be useful to label these clearly as being p, q, and r, so I can reference those. P, the first component of our vector field, is sine y. Q is x cosine y plus cosine z, and r is negative y sine z. So we want to find a function small f such that big F is equal to the gradient of small f. That means that the partial by x of small f of x, y, and z would have to equal p, the first component of big F, because that would be the first component of the gradient. That's what we're looking for. And that is equal to sine y. All right? So if that is the partial by x, that means that f itself should be an antiderivative of p, which equals sine y, with respect to x. So we have this partial integral here. Sine y is constant, so that antiderivative actually is x sine y. And we need to add some constant. But as I talked about in the previous video with the simpler case, this is a partial integral with respect to x. Any function of y or z is constant with respect to x. So let's say that the function we add is some function g that depends only on y and z, not x. Okay. So here is the beginning of a template for our function small f. Now we can say, all right, so if we take its partial by y, that will need to equal q. Okay, so, don't do that. I actually want to evaluate this. The partial of f by y, well, over here is our form for f, right? I want to take the partial of this by y. So that looks like it'll be x cosine y plus g sub y of y and z. We don't know what the function g is, but we want to take its partial with respect to y. And that will need to equal q. And what was q? The second component of f, that is x cosine y plus cosine z. X cosine y plus cosine z. All right? Now looking at this equation, we see that there's x cosine y on both sides, so let's subtract that off. So that means that g sub y of yz is equal to cosine of z. So that means that g itself would have to be an antiderivative of this with respect to y, because this was the partial by y is equal to cosine z. So if we integrate with respect to y, we should get back to the original function g. Well, z is constant with respect to y, so cosine z is constant. So it looks like we have y cosine z plus some constant, quote-unquote constant, that cannot depend on y, but it could depend on z. So let's call this h of z. All right. So now we're starting to fill out a little bit more. We had this general form for f. Let's go back and plug in what we know now. Small f of x, y, and z is equal to x sine y plus g of y and z. But we now know that g is equal to y cosine z plus some function h that only depends on z. Progress. Now all that's left is to consider f sub z of x, y, and z, and recall that that must equal r, the third component of the vector field f, because that is supposed to be the gradient of small f. So f sub z, if we look at this and we take its partial with respect to z, well, x sine y is constant, so that goes to 0. Y cosine z becomes negative y sine z. Not finished yet. And we need to also differentiate h of z with respect to z, so that is h prime of z. And this needs to equal r, the third component of our field, and that was negative y sine z. Now we see that there's this negative y sine z on both sides. We could subtract that off or add y sine z, however you want to phrase that. So that gives us that h prime of z is equal to 0. If we integrate that to find h of z, that would be the integral of 0 dz, which is just some constant, k. And that means then that the vector field we're looking for, small f of x, y, and z, is equal to, let's look at the form that we have. It's this stuff here. We have x sine y plus y cosine, for some reason my z's are suddenly falling apart. There we go, cosine z plus h of z, and h of z we just found is a true constant. It does not depend on any of these variables. So it appears that we get that potential function right there. This is, again, a fair bit of work, so we should probably check that by taking the partials and making sure that it does give us the gradient that we want. I'll do that after the next version here, where I'll just go through and show you the, one of the quicker bookkeeping methods. I'm going to do a slightly more thorough version. I will integrate all three of these. If you are feeling, particularly lazy and also slightly in the mood for maybe taking some chances, you could just integrate this middle one, because that looks like it will not be hard to do, and it's most likely to give us all the terms we need. Let's go ahead and just write them all out. So we can integrate the first component of f with respect to x. We can integrate the second component with respect to y. And we can integrate the third component. I don't need to have parentheses there, that's fine. With respect to z. And again, these dx, dy, and dz are not arbitrary. This is because we want big F to be the gradient of small f, which means that small f sub x should be this, the partial of f by y should be this, and the partial of f by z should be this. So we're specifically trying to undo each of those respective integrals. Or undo each of those respective derivatives by taking the integrals. So integrating sine y with respect to x, we get an x sine y plus something. Integrating this stuff with respect to y, so we have x cosine y, x is constant, integral of cosine is sine. We have this cosine z, that is constant, so we slide a y in there. And here, integrating this with respect to z, well, we've got this negative sign. Its antiderivative is cosine, so it looks like we get a y cosine z plus something. And now, you know what? I want to have this still be visible. So I'm going to write this up here, actually. Our potential function f of x, y, and z, we want to build something up that includes all of these terms. And we see that that is x sine y plus y cosine z plus a constant. That should be the same thing I ended up with. Oh, I skipped one. X sine y plus y cosine z plus a constant. X sine y plus y cosine z plus a constant. Okay. Now to actually check this, if we take the gradient of this, first take its partial with respect to x. This first term, we get sine y. That's that. Y cosine z is constant, so that and the other constant k go to 0, so we just have sine y. That matches. If we take the partial of this with respect to y, we get x cosine y plus cosine z. That's what we have here. Take the partial of this with respect to z. X sine y is constant. Derivative of cosine is negative sine, so we have negative y sine z, and that's what we have there. So that worked out perfectly. And you can see what I was saying about, the more complicated component, the one with the most terms, it's not hard to integrate. If you were to just integrate that first, and then just sort of check it to see, okay, take the partial by x, see what you get, take the partial by z, see what you get. It covers both of those, so you'd be, hey, done, after doing just one integral. That depends on how comfortable you are with these things, and how, how sure you are that if it doesn't work, that you know what would be necessary to maybe integrate some of these other things and find the missing terms and stuff like that. It's a little bit less directed. It's kind of, like I say, it's sort of looser. You have to be able to just kind of adapt and manipulate these things as necessary. If you like to be more methodical and careful, you can go through step by step and work these out like I did here. But we have that. Now, we are asked to use part A to evaluate the integral of f.dr. Well, we want to find the line integral along C of big F dot dr, but we have just found that big F can be written as the gradient of some other field here, a scalar field. So we can use our fundamental theorem of line integrals and just evaluate this at the endpoint. What is the endpoint? T is going from 0 to pi over 2. So we can evaluate it at the endpoint, pi over 2, and subtract the value at the initial point, 0. Okay. This is our B, and this is like our A. So we just need to find the ending point When t is pi over 2, plugging that in, we have sine of pi over 2 is 1. So we get 1 pi over 2 pi. 1 pi over 2 pi minus f at 0, and that is 0, 0, 0. I keep going up to that, but it's the same as what I have here, so let's do that. So, remembering that our our potential function was x sine y plus y cosine z plus a constant. We just need to evaluate that and take the difference. Now, there's some constant here, but we could take that to be whatever we want. It doesn't matter because when we subtract, it's going to get canceled off, right? You'll have k minus k, that vanishes. So much like we do with definite integrals, normally we just pretend that constant's 0 and just kind of evaluate without it. So we have x sine y. Do this for the first part. We have x sine y, so we have 1 times the sine of pi over 2, which I guess I don't really need to do that. I can just do this. Okay, so we have 1 times the sine of pi over 2, which is 1. That is 1. Plus y cosine z. So y is pi over 2. And the cosine of z, that's a cosine of pi, that's -1. So that takes care of f of 1 pi over 2 pi. Now we need to subtract f of 0, 0, 0. Well, looking at this, if x is 0 and y is 0, that whole thing is 0. So that's just 0. So it looks like we get 1 minus pi over 2 as our solution. Okay. So you can see we were actually given everything that we needed to evaluate this from just the techniques of the previous section. We didn't need to find a potential function. We were told to find one, but if we hadn't been told to find one, and we just needed to find the this line integral, we could just use the techniques of the previous section. We didn't need to find a potential function. We didn't need to worry about anything being conservative. No fundamental theorem of line integrals. We could just say, all right, well, we've got our vector field. We have this, we have this parameterization of the curve C. That gives us our x, y, and z. We can plug those in, take f.dr, and evaluate. And that works. It is a lot more work than what I wrote on this page. If you can find the potential function quickly, then it is much quicker and easier to evaluate it. If you instead go through the rigorous method of computing the potential function and then evaluate it at the end, then the amount of writing that you do is probably about the same as the amount of writing you would do just by evaluating it directly, but that doesn't mean it's the same amount of work. I personally felt that the direct evaluation was more work. There was a bunch of trigonometry, there was an integral by parts, it just, there's the same amount of writing, but a lot of the writing in this is just bookkeeping and is not really intensive. It's just keeping track of stuff and substituting things in the right places. There wasn't a lot of work that we did here. Evaluating this line integral directly is a little bit of work. It's reasonable, it's doable. You can do it in a page of just handwritten, doesn't take long, but it's annoying. It is way more efficient to find this potential function, like I said, especially if we can do so rather quickly. If you can quickly find a potential function and then use fundamental theorem for line integrals, you get a result way faster. And that difference can become even greater depending on the particular situation you have in terms of how messy the curve is, how messy the vector field is. In some cases, finding the potential could be harder than just working out the integral directly. It will depend on the precise nature of what you have, but very frequently this saves a lot of effort. We can't do it all the time. It only works when our field actually is conservative. So I definitely want to emphasize that if you're doing a problem like this and you take one of the shortcut methods and you just maybe do one integral to see what you get, you have to make sure, take the gradient, evaluate the gradient, and make sure you get the original vector field. Because, you know, it's possible that this is not even conservative, and in which case a potential function doesn't even exist, right? You know, if we ask you to find such a thing, then you can expect it will probably exist. We're not trying to trick you. But, you know, in more practical applications, you know, after this class, when you just have to use these things to solve problems, who knows, right? You want to check for this, because if you can use this method, it saves a lot of time, but you won't always be able to use the method. So be careful about that.